Okay, so we have the first of our assignment presentations. So we've got Danny Wen, and so you're going to talk about Grover search with 3 qubits. Okay, so you can take it away. Where do I sit? Okay, I'll come here.
So my project is about Grover search using 3 qubits. I decided to choose this topic because I thought I saw an example on IBM Q with Grover search with 2 qubits, and I decided to make it a little bit complicated. So I chose the case with 3 qubits, and do I need to push this?
No, the other way? Oh, right, yes.
Oh, so I need to open this?
No. This just needs to be in the foreground, so
Okay.
now it should work.
Oh, yes, thank you.
Yeah.
So first, let me ask you a question. If you want to find one card inside four cards, and you only have one chance, what are the odds of locating that card? Eden, can you give the answer?
What about me? What?
I think it would be quite easy for a
I think that you need to find the K in between the 4 cards.
Yes, I would have one card, which is the king. I would have it in 4 cards, and then what are the odds of finding this card with my first try?
I can't think of a method.
There will be only one king in these 4 cards, and then you want to find it, and it's like drawing a random card from 4.
Yeah, but it only has like 25%.
Yes, 25% chance of finding this king within the 4 cards. So what if I told you, if I were to hit these cards and I were to find the king, I would only use one chance, and then I will get the king 100% at a time. That sounds a little bit amazing, right?
Yeah.
Okay. Yeah. So that's basically what Grover search does. It's a little bit complicated than just drawing a card. It involves some calculation in a way, but the basic idea is kind of like that. Okay. So the platform I'm using is IBM Q, which Professor introduced this platform to us, and it's a online quantum computer, which allows users from all over the world to use a real quantum computer through the internet. And actually, some data this platform provides is actually not like real-time operation on the quantum computer. It's kind of like if your circuit is already built, they will give you the data that was stored in their database. But the data is actually run through by a quantum computer.
Oh, so if there's an algorithm that's seen before, it just gives you the data for that, or?
Yeah, to my understanding, it's because it's always like the same result, and there's no like fluctuation. So
Okay. So only if you give it a brand new algorithm.
Yes,
will
if
it
your
actually
algorithm,
go and calculate.
it's
Okay.
So this is basically the interface of IBM Q. Here you get some. This is a composer. I usually use a composer. This is some quantum base that you can use to build your circuit, and here's these qubits that you can add and delete. I think you can add up to 8 qubits, but I never used or more or even more, but I never used that much. And here under this bar is I think important part of this quantum computer. It shows the results in very clear shape. One is the probability, the other is the Bloch sphere state, and over here is the I think it's the coding part. I never used this part in my coding because this is the same as dragging gates and putting your circuit together with these quantum gates. And in order to code, you need to understand like what is the code for each gate. So to me, it's more simpler using like dragging those gates around. So in my quantum circuit, I use a poly X operator, which is simply this matrix. I think it's actually equal to the not matrix here, which is this. But at the time I did it, I didn't fully comprehend this quantum gates, so I ended up grouping two squared X together to make a poly X operator and use them in my circuit.
So you defined that yourself?
Yes, I grouped them together and defined it myself. Yeah, and from here we can see that starting with the qubit at the 0 state, after the poly X operator, we get a qubit in the 0-1 state.
And for that Q sphere, which I guess is the Bloch sphere,
yes.
Like how do you change which qubit you are looking at? I didn't do that.
Yeah, I think you can drag it around and
because like that one I guess is for the first qubit, right? And this is you've got two qubits, and the other one is always in
I think
in
this
zero,
is
right?
in 0 position. This is the 0-1 position.
So that's the whole. Oh, okay. So there must. I guess they're using a more generalized Bloch sphere, right? Because when we did the Bloch sphere,
direction. Our Bloch sphere.
it's just for one qubit.
Just for one qubit. Yeah.
But this
Like
is actually for more than one qubit.
Yeah, I think they even have a block this sphere for 3 qubit or 4 qubit gates or even more, and they have different different positions on the sphere.
I see.
As an indicator. So like my goal is first to break down their Grover's search with 2 qubit and like apply their similar methods to a 3 qubit case. So this is actually a circuit for the 2 qubit case, and this is not what like the this is not what the IBM Q instruction provided. I use my own operator. It functions just like a NOT gate, and I'll explain the circuit and how it's built, and so we can apply this method for the 3 qubit case. So here we are trying to do is basically like putting the king into these 4 cards. So like we first need to put some information into the circuit, and then we can try to use our Grover search to locate this piece of information. So what I'm doing here is creating a superposition using the Hadamard gate, and then I'm using another Hadamard gate and the CNOT gate and another Hadamard gate to encode this message into these 2 qubits. So you can see from the end result, they are actually the probability of them is actually the same. But what this operator does is that it has its information embedded in the last qubit.
So that's the oracle, right? So
Yeah, that's
Hadamard,
basically the
control node, Hadamard, all that together is the oracle.
Yeah, so yeah, this part is the oracle. The superposition is just like it's making it into starting point. Yeah. And after the oracle, wait, I think this circuit is actually a bit. I think this circuit is actually not the correct case because we shouldn't have these poly X operators here, and the poly X operator should be over here.
Yeah, those X's will actually do nothing because
the Hadamard gate is
it's the eigenstate, so it'll just add a phase. So actually they'll do nothing anymore.
Oh yeah, so
it's safe.
it could be deleted. It's better deleted. And so here we are actually using these two operators to find the state. And what this poly X operator and Hadamard gate does is, I guess it first flips the two states of the Q0 qubit, and then applying a superposition. And after that was another Hadamard gate and CNOT gate. So this is you can consider this as a whole. So this part is actually the Grover search algorithm. And
so the second stuff there, all that stuff is the thing that flips the sign on the 0, 0, on the plus plus state, that other operator.
Yes.
Yeah.
Yeah. So that's actually the only functioning part here, which does the work is this part. So we try to apply a similar method to the 3 qubit states, and
hold on. So did it work? The 2 qubit? Yeah.
Yes, the 2 qubit state. Here's I'm sorry, I skipped the result part. So here we can see we've hidden the information into one of these states, and from this operator we know it's the 1-1 state. You can actually hide it in either state. For example, if you change this to I think a NOT state here and the control state here, it will be hidden in the 0, 0 state. So from the Grover search, we can find the probability, which is the probability is 1 in the 1-1 state. So the information is hidden in the 1-1 state here. So in the case of 3 qubits, we are again creating a superposition with the Hadamard gate, and then hiding the information on the 1-1 state with a Hadamard gate and Toffoli, I think it's pronounced Toffoli gate, and then another Hadamard gate. And this is the full circuit for Grover search in the 3 qubit case. And this is the oracle here, which hides the information, and this part here, the remaining part is the circuit, which does the actual search, and it's very similar to the 2 qubit case, and we use the Hadamard gate and the poly X operator to first to create a superposition to I think here it's actually reducing the superposition and then changing the and then flipping the two states within each qubit, and then we use the Hadamard gate and the Tollef gate to pass the information to the last qubit, and after these steps we can get the result that the probability is actually all in the 111 state.
Yeah, so it looks actually like the Hadamard and then 3 X's. This looks like the thing which
yes, I think
is the thing that puts the phase on the 0 state. So remember, like from when I was, we haven't done the lecture yet. Okay, but like in Grover's algorithm, there's like you do oracle and then you do the other thing which puts the phase on the 0, 0, 0 state, and then you keep on repeating those two, and then so it looks like the 3 H's and the 3 X's is the other gate. Is that?
Yeah, that's what that's what the circuit is about.
Yeah.
But like the way this IBM Q is constructed, I couldn't like separate these two, the oracle and the state clearly. So what actually does the search is this part, like the three Hadamard gate and then the poly-X operator, and then this Tollef gate here. So that would be much more clearer if like I separate the oracle and the part that actually does the search. So it's actually very because here it's all linked at one place.
Yeah, I can understand that.
Yeah.
But actually, I thought that the other operator also needs something like a Toffoli gate, or so it's actually quite interesting that this works. So it's actually not what I would have expected. Like for the other operator, the Toffoli and the Hadamard, I totally agree with you there. But then the 3 H's and the X's is not what I would have thought would work, but actually apparently it works. So you might have actually found a slightly different way of doing
So
it.
it's kind of different than our like the Grover search.
Yes, it's actually a bit different, I'd say. Yeah.
I'll have to.
Well, that's cool. It's unexpected new results. So cool. I mean, it still works, right? It totally, absolutely works.
It works very well. It's
Yeah.
like all the qubits are like all the probability being using the last qubit. And so further further on the result, this is actually the all the probabilities combined, and you can see that it's actually not like 100 and 0 and 0 and 0. There's actually some probabilities on the other qubit case as well. This is actually kind of confusing for me because in the 2 qubit case, if you can check it out here, there's actually like this probability is actually 0, and like the test results shows that they're 100% on the 1 qubit. But at the 3 qubit case, we are actually seeing some probabilities on our other qubit as well. And for the sphere, for the Q sphere, I'm not gonna lie, I couldn't really understand what is going on because it has many it has too many states, and that's a bit confusing for me.
Yeah, actually, I also don't understand it because actually this block sphere representation is like I think it's generally not so easy to extend it to larger spaces. It works for one qubit, but then for
Yeah, one
other
qubit
things,
kind
it's not really an exact. I don't know, or I don't know how to really do it. Maybe they just sort of made a, they just equally distributed all the orthogonal states on the sphere.
Is it like a projection from a four-dimensional space?
No.
That would be even harder to understand.
That would be smart, but I don't know how they would do that. So, yeah, maybe it's nothing. Maybe they just made it up.
Yeah, but I think the probability cases could illustrate the results pretty straightforward enough for me. So I always kind of just look at the probabilities.
Yeah.
And this result here actually in the test case the actual result is in numbers is actually here. So for the all the other states except the 1-on-1 case, the probability are all 0.78125 kind of percent. This I found quite interesting as well, because I originally thought that these were all the other states were just like computational errors that generate from like computer tests, because I guess 3-qubit they should, like, it's much more complicated than 2, and they would actually have some test errors. But the probabilities is actually all the same, so it got more confusing from that. But aside from those errors, which to this point I'm still not very I still don't really understand how they occur, and like how much how did they end up all being the same one. The test results is actually had 94% case about 94% cases are in the 1-1 case, which is really good. So we arrived at our conclusion that with the Grover's algorithm we were able to find the hidden quantum state with relatively simple procedure, and like just basically you can just find one thing, like with your first chance, like do some correlation with your like first shot, and which is really amazing to me. Imagine like if you play poker with that and you just randomly draws one card and say, yeah, I found my card. Yeah, so this is my assignment and my presentation. Thank you for listening.
Great. Yeah, very nice. So yeah, I mean regarding the percentages, yeah, that one.
Yeah.
So it could be because, so actually in Grover you have to repeat this block, this oracle, and then the other thing, and then you repeat that several times, and then what it does is like it gradually changes the initial state, which is a superposition state, into the final state, right? But it does it in kind of discrete angles. I'll talk about it in the lecture. And then so maybe it just it doesn't quite get the top of the probability, maybe because it's kind of discrete, it just kind of misses it. So it might be because of that.
So it's kind of like separated into each steps, and
yeah, but basically because with each pair of operations that you do, it gets some angle closer to the real result.
oh, so
But then if that angle isn't like exact, like multiple of pi or something, then it might just kind of miss it, right? Like maybe for the 2-qubit, doing 2 exactly gets it like perfectly.
yes, because when I add more, like at the more when I add more of the similar operation, like repeating those steps, the probability actually kind of fluctuates around, like sometimes it increases, sometimes it decreases, and
Oh, really? So sometimes it's not exactly this number?
yeah, when I had so this circuit is a really good case. So because like the 1% the percentage is really high, so I choose this as the presentation case. But actually I like skip some circuit here, and when I try to like compute that percentage, so the each of the others they have a relatively higher percentage than this case.
I see. Yeah, right. Yeah. So yeah, I think that's consistent with what I was just saying. So doing a certain number of these ones, you need to get the certain number right.
Yeah.
If it's too few, it will not be
as good
at the maximum. Yeah. And if you do too many, by the way, it also overshoots, and you actually get worse results. Yeah. So, but just the fact that these numbers are so exactly the same, maybe is this maybe the simulator of the quantum computer, or is it the actual quantum computer? Because I think I know that there's a simulator, and then there's also the thing that you actually can run.
I wouldn't be surprised if it's the simulator, because they're all like so even, like evenly distributed. So I imagine the real computer you might get some like I don't know, maybe one case will be higher, another will be fewer. There's kind of distribution on the probability there. But they're so even, so
so
it's also kind of confusing.
So maybe, I don't know, I've never personally used it, but maybe you need to I don't know, apply for a different account or something. I don't know. But anyway, I think it's great, and I think I'm quite interested in this new gate, this other gate, which is I think not the usual one.
You mean this?
The 3 H's and the X's.
This gate.
Yeah, so that thing. Yeah. I would be interested to know why that actually works, because it's actually not the one which I would have thought. Yeah. So well, if we have time, maybe we can look into it. But yeah, very good. Yeah. Any questions, Elin?
I'm also wondering how the 3H gates can perform this search.
Yeah.
So is there a computational proof of that?
I did some like computation in matrix when I was like figuring those gates out, and I kind of just understand them as like the first they first changes the superpositional state, and then they kind of flip each state, and if the state has information, it gets flip around, and with like which was like each state flip the information in turns ends up at the last state there. I guess I could look into the computational proof of the why does the search actually works. And
I mean, probably the way that I would do it is just that I think I'd figure out what the eigenstates of that combination is, this H and X thing. And because they're individual qubits, it's actually just a 1 qubit calculation. And then maybe we can work out something from the eigenstates, because there's kind of a couple of ways of looking at this Grover's algorithm. And there's another way, which of course I'm not telling you in the course because it's sort of beyond, but like energy transition. So actually almost no way it gives this interpretation. I wrote a paper on it last year, so it's...
Can we see that?
Yeah. Yeah. But basically, it's like, if you think, remember these unitary gates originally are some Hamiltonian, right? And then the Hamiltonian is something that tells you something about the energy, right? And basically what this Grover does is to, you can think of it also as some energy transition between its initial state. So what this second gate, your triple X, triple H one, is supposed to do is to make a state which, maybe I'll draw it. Yeah. So another way to view this is for your 3-qubit case in energy space. You have basically all these states which are at 0 energy. So it's like 0, 0, 0, 0, 0, 1, and then the last one, 1, 1, 0. And then there's this state, 1, 1, 1, which is your target state, and that's at energy 1. And then, okay, this is not really proper, it's not quite proper, but just to give you an idea. And then this, so your triple HX thing is supposed to make this energy 1. And then this other thing, actually with the Hadamard's, so this is your first one. Sorry, that's your first one, that's your second one, right? That thing is supposed to make this energy 1, 1, 1. And then what's supposed to happen is that this is, because it's at the same energy, this one gradually turns into this one. And all these other ones haven't got the right energy. So that's why this one wants to turn into that one and not any of these other ones. This is sort of another way of viewing Grover, right? And so I think what might be happening is that this thing is probably something that makes this state with energy 1, even though it's not the usual one that that's in the textbook.
Reduces the energy from all the other cases and then just leave behind the...
Yeah. So somehow, maybe your energy landscape might not look exactly like this, but then it might effectively just do the same thing anyway. Like maybe your energy landscape looks a little bit more like some of these other states and not at 0 and whatever. But it maybe doesn't matter somehow in the end, because your so long that your initial state, this one, is at energy 1, and this one, that one for sure does this, right? And then so it does the transition anyway. So even though it's not the same thing, it still works. Still works. So that might be the way to look at it. But anyway, yeah, that's great. Any other questions? No. Okay. Great. Thank you. Okay. Yeah. So I don't know. I think it's quite nice actually to have these assignments. Because it's not just me talking at you all the time, and you can sort of find something a bit new sometimes too. Okay. But having said that, let's go back to the lectures. So it's been a little while, so let's recap where we're up to. Okay, we all know what Grover is, searching a database. That's right, we were talking about the oracle, and so we have a function that is finding these desired elements, so a king, as Danny was saying. And we're going to use the same kind of construction as in Deutsch's algorithm. And yeah, and in a way, actually, you don't really need to do this construction because essentially what you want at the end is some operator that kind of gives this kind of relation. Right? So this, if you have the solutions to the problem, so this x, these are all the states, and this is a multi-qubit state that goes from 0, say 0, 0, 0 to 1, 1, 1. That was the case that we were just talking about. And one of these ones, which was the case in Danny's assignment, acquires a -1 phase, right? And so essentially this whole construction is there just to create this effect. And so we could have equally just started with actually this one, because the reason, if you remember the reason why we were talking about this, is we kind of made this thing to ensure that it's like a unitary reversible gate, right? But actually this is a perfectly reversible unitary gate anyway. And as in Danny's example, in fact we didn't even use this extra qubit to achieve it. You can just use some kind of gate to make that minus sign. So, I don't know, you could say it's sort of a historical artifact, or, why do I bother talking about this? It's probably because when it was first conceived, discussed, it appeared in this form. But I think strictly speaking, it's not completely necessary. You could just start with this. Okay, so basically, henceforth, we're going to forget about this ancilla qubit because we just want that -1 sign, and so we're going to find the oracle as just some operator that puts a minus sign on the state that we're looking for. Right, okay, so this is where we got up to last time. So that was one of the parts that we need for Grover's algorithm. And there's another operator, which I'm calling the phase inversion operator. And this one is a lot like the oracle, except that it always just adds a phase on the 0 state. Okay, so just the 0 state. And the oracle, this is dependent on the function or the problem that we are solving, right? So, depending on f of x, you'll have a different distribution of minus signs. But this one is always just this one, and it's always just on the always on the 1 state where x is 0. And by the way, when I write x is 0, I mean x, this qubit is like 0, 0, 0, 0, like this state. So, for example, if I had this 2-qubit example here, if I start with some initial state there, that's the arbitrary initial state, then what that does is to add a minus sign there. Okay, so that's the V0 phase inversion operator. But what actually we normally do is we surround this thing by Hadamard gates. And basically what this does is to change the basis of this whole operator. So over here we're just working in this 0-1 basis. This is usually called the computational basis because 0-1 is like the digital kind of basis. So if we put Hadamards before and after this operator, what basically that does is to change the basis of this so that it's not the computational basis that we're dealing with the 0, 0, 0. we actually rotate the whole thing to this plus minus basis. So instead of writing, so basically the difference is so the V operator, so if I have my input states X, so I'll just do a 2-qubit example. So basically the phase that we can have is, so the phase will be like this. That was V0, right? V0. The rotated thing, essentially we're working in the plus minus basis. Maybe I should do that for consistency, and it's exactly the same thing, right? So it's just only that plus state that gets a minus sign, and everything else has just a regular plus sign. So the first one has a minus sign. Okay, so that's sort of the second thing that we're using, and this is the thing that we were just talking about with Danny's case. So this V, what Danny had as V was basically this thing here. I believe that, yeah. So I think that doesn't actually do this, but it must do something kind of like that because it still works. So yeah, so that'll be interesting to figure out in what sense it's similar. Okay, so then Grover's algorithm goes like this. So we have those two operators. Well, okay, so we start with making full superposition state here. So if we applied 0 Hadamard's everywhere, then initial state Hadamard's everywhere. Basically, at this point in the circuit, the state is like plus plus plus, and plus 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 is of course well, okay, 8 0 0 1 all the way to 1 1 1. So it's a superposition of every possible state. And then we apply this oracle, and that will change the sign of the target state. So in Danny's example, it would change the sign of that one, 1 1 1. And then V, for V, it will flip the sign of plus plus, or plus 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 state. So because if after the first oracle, this state is actually no longer plus, right? So we actually have to work out what this does. So it's not obvious just by looking at the circuit what is going to happen to this. In fact, requires a little bit of a proof. So I'm not telling you on this slide, but I'm just telling you what the whole scheme is. And if you repeat this OV combination some number of times, and this some number is the square root of n, this is the size of the database. So in this 3-qubit example, that would be 8 to the power of 3. And m is the number of solutions that we're looking for. So if we're only looking for the 1 1 1 state, like we were for this example, then that would be 1. Okay. So in other words, for the 3-qubit example, we would repeat this square root of 8 times. Square root of 8 is what's square root of 8? 2.8. closer to 3 than 2, right? How many times did you do your, how many repetitions did you do? Did you do 2 or 3?
I think it is 3.
3, okay, so there you go, makes sense. But it's not exactly 3, as we can see already from this formula, because it's square root of 8, right? So it's actually slightly less than
2.8.
Yeah. So yes, exactly. Yeah, 2.8. That's right. And of course, you can't do it 2.8 times. You have to either do it 2 times or 3 times. So 3 is the best number of times to do it. Okay. All right. So that's the algorithm, and then eventually you measure it at the end, right? Okay, that's the algorithm. But how does that work, and why does that work? So, okay, so I already wrote that, but let's go through the algorithm step by step. So after the first set of gates, you just create the superposition state. Okay, I've already said that. And this, I've drawn a red line here, so you might be able to see that's where we're up to in the circuit. So next we apply the oracle. And the oracle is going to flip the sign of the solution states. And so what I've got here is something a little bit more general than what I was saying just here. Because there might be more than one solution. So it might be that, so remember, n, this n here is the size of the space, but m is the number of solutions. So if there's more than one solution, then this algorithm actually finds sort of all of them. Well, in a sense. Okay, so we're going to define these 2 things. So basically, these are just all the states that are not the solution. Sum of all the states are not the solution. These are all the states that are the solution. So just to give you an explicit example, so if basically if we're doing Danny's case, then x not solution would be equal to square root of 7, 0, 0, 0, all the way up to 1, 1, 0, and x solution, that will be just 1, 1, 1. Okay. There's more than one solution, like say if there's 2 solutions here, then we need to normalize it, so it's 1 over square root of 2. And this is 7 because obviously there's 7 states, and we need to normalize it. Okay, so then we can write this initial state actually in terms of these 2 things, and it turns out that this will be the best way to write it. So even though it looks a little bit more complicated, we can write it like this. And so in this case, the initial plus state, and because we've got this, square root of 7 thing here, we need to multiply it by the appropriate factors in order to have just this equal superposition. So the initial state, in terms of these 2 vectors, you would write that as square root of 7 x not sol, and then this is x sol. And then after we've multiplied by the right coefficients, we need to divide by the overall normalization. So that's just that thing there. Okay. Then we're going to apply the oracle. And so now that we've written it in this way, it's actually easy because, well, particularly this step is easy because we know that the oracle, it just flips the sign of this one. So oracle times plus 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 is going to be just same thing, not sol, minus x sign of the solution part. Slightly better ping. Okay. All right, and then now let's do the, oh, yes, that's right. So there's a great way of understanding what this operation does geometrically. Okay, and so let's, and it turns out that in Grove's algorithm, you can write everything in terms of these two states that we just defined. So the whole thing evolves actually in this two-dimensional kind of subspace. Obviously, the larger Hilbert space, or the larger space, is much bigger, right? So it's 3 qubits, it's 8-dimensional. So normally, the algorithm would be moving in this 8-dimensional space, but actually, for Grover, it turns out that it's entirely in this 2-dimensional subspace. So we can actually just draw it quite easily on the plot here. These things are orthogonal, and you can tell they're orthogonal because there's no common states, right? So this is the solution one, and this is the not solution ones, right? So obviously 111 does not appear here, and all these states do not appear here. So if you take the inner product of these two, it'll be 0. So they're orthogonal, and we've normalized them properly. So those are our axes that we're going to work with. And let's just talk generally of what this oracle does. So if we take some state, which is some superposition of these two basis states, and we apply this oracle, so if we start with a state AB, it's pointing that way, then this flips this sign, right? So obviously, what that does is to reflect it along with the axis being this not sol. So we can use that to kind of visualize what is happening to our state. So, okay, sorry, that's not what I'm explaining here. Okay, so hold on. So let's just sort of sketch what's happening to our state here first. Okay, so let's sketch this. So this is not sol. This is not sol. And this one is the solution. Yeah. Okay, and our initial state looks like this. And keep in mind, there's no complex numbers or anything, so it's just all real numbers. So we can just literally kind of plot it on this graph. So, for example, here, this coefficient here is root 7 on 8. So, it's quite close to 1. This coefficient is 1 over root 8, so it's kind of much smaller than this one. But it's not 0. Okay, so if we plot it along on this graph, then roughly speaking, this will look like this. So this is actually what the Grover's algorithm initially starts with. And then one application of the oracle, what it does is, and so this in this triangle, just to so that we've got everything clear. This is root 7, 8. And then one application, the oracle, will bring it down below this axis here. Okay, so that's where we're up to at the moment. We've applied the oracle once. Okay, now let's think of what this V is going to do. Right, and if you remember, V is actually, kind of something very similar to the oracle, except what it does is to apply a minus sign on this plus state. And I don't want to show you the calculation because it's just sort of tedious. It's not very interesting, and it's kind of obvious from this result that so the oracle is something that flips the sign on the solutions, right? And basically what that does is to reflect it around this axis that was the not solution, right? What the V operator should do is actually to again reflect it around actually this axis, which is this plus. So it will, for any state over here, it will then reflect it and make it another state which is on this positive side, because, well, okay, so here, maybe I should have said minus B dash here and plus B dash to be a little bit clearer. But basically what this does is to reflect the state around this plus state instead of the not sol state. And this is basically because the V and the oracle are, kind of very, similar operators. They're both operators that just change the sign of one particular state. In the case of the oracle, it changes the state of this solution state. In the case of this V operator, it changes the sign of this plus state. So, that's the action of this V. So essentially what you can then do is to, purely from geometry in this sort of two-dimensional space, you can just think of the multiple reflections that this initial state is going to do. So our initial state, this was our initial state, and firstly it gets reflected around this not sol axis, and then, so that was the oracle operation, and then it will get reflected now around this plus state axis. So now this is going to go up here, and now notice that the angle between this kind of green line and this other line going down is actually theta, right? And when we do the reflection, this will end up pointing in this direction, with the theta being this angle between the green axis and this arrow here. So if you think about what happens after one iteration of OV, it'll sort of go down by a degree theta. The theta is defined somewhere over here. And then it'll go up by 2 theta. So if it goes if it's rotating clockwise by theta, then anti-clockwise 2 theta, of course, eventually it will end up closer to this red axis. So it's a purely argument based on sort of geometry, but this is sort of the easiest way to kind of understand or kind of prove why this works. Okay, so regarding these equations here, this is just a definition of what this angle here is. So in this particular example, the angle was, you just look at this triangle, so whatever that angle is what theta is, or rather this is theta on 2, right? So this is theta on 2. So that these factors just define that triangle according to just high school trigonometry. And then all I'm saying here, this is like this initial state plus, just written in terms of cosine sine, because we just define theta here. So that's just that. And we know that after one oracle, then that sign flips, but then after application of the V, it will go up by another 2 theta. So eventually the angle here is going to be 3 theta over 2. So initially the angle was theta over 2, and then after the VO operation will be 3 theta over 2. Just looking at this diagram. Okay, and so basically the pattern then repeats itself because, you know, this is just, you can just work it out according to what the combination of these two reflections are. And so essentially with every pair of this OV, it basically moves closer to the solution state by an angle theta. So by repeating this some appropriate number of times, it'll get quite close to this solution state. And so this is what I was saying at the end of Danny's talk, that, you know, maybe the reason why it doesn't get exactly to 100% is because these steps are kind of discrete, right? So this theta is, you know, whatever you work out according to here, right? So you just work out that angle. So if that angle isn't, you know, a multiple, you know, if you don't do a multiple, yeah, if it's an angle such that it's not like, it doesn't get exactly pointing along this solution direction, then you won't get 100% probability or 100% in this solution state. You know, you'll get it kind of, you know, kind of closer, like, so maybe after, so one iteration it'll look like here, so this is theta, right? And then 2 iterations, well, according to this, it'll, you know, it might not point exactly along the axis. Okay, okay, and then now here comes the most important part, which is, so how many times do you need to apply this? Okay, and because we know this angle, so basically if after k applications of this VO, essentially we want this thing here to be 1, right? Or we want that angle to be pi over 2. Then sine is 1 and cosine is 0. So we obviously want the state to be in the solution and not in the not solutions. Right? So, okay, set that to pi over 2, simple calculation, and work out what k is. So if you just rearrange this thing according to the definitions, it's that, and just to make the formula a little bit nicer looking, let's assume that n is quite big and m is much smaller than n. Then this inverse sine is approximately, you know, linear. So this sine of the square root of m over n is approximately just square root of m over n, and then you just forget about the factor of a half, because let's say that's small too. So it's equal to that. And so the key thing here is that this is scales as the square root of n. And classically, you need to search through the database, like basically almost all the database elements, even if you're doing a random search. If there's 100 elements, roughly speaking, you need to look 100 times before you here, if we count how many times we are doing this OV combination, you only need a square root of n times. So if you had 100 elements, classically take something like 100 tries to figure it out. With quantum, you can do it with 10 iterations of Grover. If n is bigger, then this gets even more kind of powerful. So even though this is, inverted commas, only quadratic speed up compared to classical, but if n is big, then this can make a big difference. So if we're talking like n is 2 to the 50, why did I choose 2 to the 50? Probably because maybe this is like the largest size quantum computers that are available today. So that's just, today's technology. So they're actually not quite good enough to do this algorithm with 50 qubits, I think. But even if they were, there would be quite a big speed up because 2 to the 50 is quite a big number, it's 10 to the 15. But the square root of n is only 10 to the 7. And basically anything like, like computers or like, gigabytes, terabytes, this kind of thing. So 10 to the 7 is, is actually nothing with, terms of today's sort of classical quantum, classical computing technology. But 10 to the 15, once you get to things like this, even the best supercomputers in the world find it difficult to handle that. Like just to store that amount of data, or just to have that in the memory of a program or anything like this, it's kind of goes beyond typical capabilities. Another factor is that this thing it's very versatile. So searching is a very generic kind of problem. It comes up all kinds of places. So it's very applicable actually. So you can apply it to optimization problems and so forth. Now, I don't know if you guys are, this P equals NP kind of thing?
I've read it in the alphabet, but I don't actually know how it works.
Right, so this is a famous kind of unproven conjecture in computer science. So there's different classes of algorithms which are some types of algorithms are very efficient. They can be solved in polynomial time, and some types of algorithms are very difficult in the sense that the time to do the algorithm scales exponentially. And so it appears that there are kind of two different classes of algorithms, right? So there are these ones which just scale much more, like exponentially, and there are those which are somehow easy. So the polynomial ones are called P, and then the exponential ones generally are in this NP class. And this P equals NP problem is, it's basically widely believed that these are different classes. Like basically, these are not the same, but yeah. So basically, it's a kind of a conjecture to say that basically, the NP class is a larger set of problems than P. So P should be a kind of a subset of NP. This is sort of the conjecture, but there's no real proof for it. Right? So nobody can prove it, but that's what is sort of observed. So one point is, could this be used to help solve such exponentially scaling problems? So the answer is basically still no, because if you have some problem that sort of scales as exponential, so say the time, say, complexity of an algorithm scales, suppose like exponential n, right? And if you apply Grover's algorithm, then essentially what happens is that it becomes square root of the exponential of n. But actually that's still exponential. So because square root of e to the n is still exponential. So it doesn't really change the complexity of the algorithm. Of course that helps quite a lot because it makes it n over 2, not n, right? But the thing is that there's lots of different algorithms that people have come up with to sort of, so even if a problem is exponential, to have exponentials that scale like relatively well, right? So essentially, even if you applied Grover, this would have to beat whatever some other potentially exponentially scaling algorithm, and essentially what we're competing here is this sort of factor in front of the n. So so here we might get a factor of a half, but maybe with classical, with a clever algorithm, you can still get some similar factor, which is also maybe like a half. So this doesn't necessarily beat any classical. This is not a recipe to beat any classical algorithm, but it could be used, right? So it really depends upon the particular algorithm, and maybe this could be used. Yes, and I won't go into it sort of out of time, but you might be wondering, okay, that's so we have to apply this some number of times. How do we know what number of times to apply it to without doing it many times? And actually there are some algorithms out there that are known to figure this out. So there's this so-called quantum counting algorithm, which, well, you can look up in the textbook, Nielsen and Chuang. So they do exist, so that even that is could be calculated with another algorithm, or you could do it sort of somewhat experimentally. Okay, all right, so we'll leave it there. Any questions? No. Okay. All right, then that'll be it for today.
Do we have new things for next lecture?
Next lecture? Well, yes. I wrote a couple of new slide sets on density matrices.
Mm-hmm.
So these are like mixed states.
Mm-hmm.
I thought maybe that could be a good thing just to do. So there's 2 slide sets there, and then there's still the wave function thing. Okay.
Can you explain more about how those operators, like the I can't remember, but it's like a rotation operator or something.
Oh, okay.
I mean the real meaning behind those operators.
Okay, all right. Maybe next lecture we can have maybe a sort of a revision session next lecture, and then once we're fine with that, we can start with density matrices. Okay.